Today, I would like to report on some observations François and I made on stream reasoning. We have found some very interesting links between stream reasoning and the concepts of backward reasoning and forward reasoning as they are known in logic programming. And I will do so by first giving some short motivation and define some terminology. Because I understand in the community, everybody defines streams and stream reasoning, stream processing a little bit different. Then I will talk about backward and forward reasoning. I'm pretty sure that everybody knows it, but to refresh the mind, that would be a worthwhile thing. Then I will present stream reasoning as we understand it. And finally, I would like to talk about database updates which originate from stream data. So first of all, how I define a stream. A stream would be a never-ending sequence of timestamped data, and this is important in the course of the presentation. As a stream processor, I understand a set of stream listeners, that is a set of processes, and these processes answer queries, queries that are directed at streams in a way so that these stream listeners can detect certain patterns which are interesting. And as a stream reasoning, I understand a stream processor, which is being programmed in a declarative manner. And this is interesting because as we found out, most stream processing applications are declarative in their nature. So a declarative way of programming stream reasoning systems which would be very much appreciated. And as you know, logic programming or automated reasoning in general would be a good way of declaratively defining things. So we emphasize on logic programming in this presentation. And also most streams are usually or imply a distributed context. This is also something that we are very interested in, although I will not expand on this particular point in this presentation. First of all, I would like to talk a little bit about backward reasoning. Backward reasoning is well known in logic programming, and it's a goal-oriented reasoning technique. The idea is that you have a large query, and this large query cannot be answered right away, but this large query is recursively decomposed into subqueries. And these subqueries are further decomposed until these queries can be answered trivially. And the interesting thing here is that only those intermediate results which are actually contributing to the answer of the query are derived. So there is no extra work to be done. And this is the reason why backward reasoning is the method of choice when performing queries on a database or in a Prolog system. And it's really nice when the data is kind of fixed and you're asking a lot of different queries, so the queries change. However, stream processing is not about databases or it's about Prolog. Stream processing has the orthogonal requirements. In stream processing, the data is kind of fluent and the queries are kind of fixed. I mean, of course, in streams, queries can also come and go, but in contrast to data, queries are kind of fixed. So backward reasoning is not the best choice of performing stream processing. The reason is when you actually try to use backward reasoning on a stream data, then you will discover that a lot of answers need to be rederived. Or if you don't want to rederive answers, so put in the computational effort every now and then you need to persist the answers to some queries into a database or by some other means. For example, in Prolog, it's done with the form of tabling. And tabling is a kind of forward reasoning. So it would be perfect or good idea that we look at forward reasoning on the next slide. So let's do this. Forward reasoning is a computation of immediate consequences from already known facts. And this computation happens stepwise, which is kind of advantageous for stream processing because, as you remember, streams consist of a never-ending vector of elements, timestamp data. So you have discrete elements in your stream, and so the stepwise inference of immediate consequences is a perfect match for stream processing. So forward reasoning kind of resonates with stream processing. And forward reasoning does not really take into account the queries, but it's more data driven. The queries are not that important in forward reasoning. You just derive what's possible, what are immediate consequences from your already known facts. And so also in this respect, forward reasoning seems the best choice for a stream processor. Interestingly enough, we don't really need backward reasoning in the first place when we have forward reasoning, because a backward reasoner can be very easily implemented on top of a forward reasoner. And since forward reasoning seems the top choice for a stream, well, we don't need backward reasoning in the first place. So how do we understand a stream reasoner? We understand a stream reasoner as a system of two components. The first component would be a database. This database would contain mutable and immutable data, but also database queries. The second component of a stream reasoner would be the stream itself, which consists of two things. First of all, the stream proper, that is the never-ending sequence of timestamp data. And also, streams store stream queries. And those stream queries refer to possibly a database if the database is not empty, and also to a temporally limited portion of the stream proper. Why is it important to have this stream proper limited in a temporal fashion? Well, the stream proper is a never-ending stream, and without a temporal limitation, we could not give an answer infinite time. So it's important to have here this temporal limitation in place. But this is very abstract, so I would like to show you an example that I've prepared. I would like to talk about a flight reservation system. Let us assume we want to determine a price P for a particular flight F, and we want to do it in a way that this price depends on two things. First thing would be the number of already transacted reservations, so the people already bought a plane ticket. And we would also like the price P to depend on the number of interested customers. Observe that the number of transacted reservations would be most probably stored in a database, because you want to have this data available forever, or at least the flight took off. But the number of interested customers is a very volatile data point, because customers can become interested, customers can lose interest. And so the number of interested customers is most likely to be represented as a stream. And when you can write stream queries, also referring to the database, you have basically all ingredients to perform proper queries on both the data in the database and the stream queries. For example, here the number of reservations for this particular flight F would be stored in the variable NVR, and the number of interested customers for a particular flight F would be stored in the variable NBI. And so you could combine database queries and stream queries and provide a new stream, a price stream for flight F, and depending on some conditions. So this would be a very natural way to write stream queries, and it's very similar to a Prolog program, except that the reasoning system is very much different. And as you can see also in this example, these stream queries need to be evaluated in a stepwise manner because, well, the stream consists of a series of data points. So finally, I would like to address one limitation that this system currently has. That is that queries are declarative in nature, and so with queries you cannot really update the database. However, this would be a worthwhile thing because it could happen that you observe some things in a stream that you would like to persist into the database. So we would propose to have an update language based on this query language. And this update language can be very simple. For example, plus p of x and y would insert, and minus p of x and y would remove all the facts p of x and y for the bindings. And those bindings x and y could be determined by the query q of x and y. So that would be a system that we envision, and we have already built some parts of this. Of course, we are open for discussion, and we would really like to have your input on this. With this, I would end here. Thank you very much.